Okay, Professor Z, this is the long-awaited week 3 assignment. So starting off, my first uh, section of code is solving linear equation systems with NumPy. So this first block is just installing our libraries, WRDS, Pandas, NumPy. Here, block 2, it's connecting our WRDS account. So here I could have replaced it with my username, but I need to input my password anyways, so it doesn't really bother me just to type in my username and password. So once that's accepted, it gives us the successfully connected WRDS. If it doesn't work, it says connection failed, which I had trouble working with WRDS. We can get into that later. So that did come in handy. And then here, define my date range. Couldn't get it to work with 2024 data. I wanted a full year, so I just, simplicity's sake, decided to do the 2023 fiscal year. Fetching our unique perm nodes, or however you pronounce that, or stock data when it's stuff with at least 20 days. Trading, and uh, this is using the SQL query to fetch these stock identifiers from their CRSP database between our dates, and then it groups them, lists our criteria, and then I wanted the top 50 actively traded stocks. Room for improvement here is I don't have the list of the stock names. They're just known as this placeholder permno, uh, whatever this is. And so it's the stock data, but we don't know specifically which stocks. So this is validating if we got the right stock data. Excuse me. If we got the right stock. If we got the right stock data. And this is giving us our date format, daily return, price, and shares outstanding. Once again, from their database. And then order it by the dates. And so it's ordering it by start and end date, but here it is converting it into a usable format. Yeah, let's place first few rows in the data. So handling missing values with the forward filling and backward filling. Here, that is just basically dropping the remaining rows of data that have no information in them. So if we're talking about forward filling, that's going to be if we have, say, 1, 2, blank, blank, 5, we're going to fill in these two blanks with the number 2. And so that's going to be the forward filling. You take this number and then you fill in the missing data. If we have like 1 blank, blank, 4, 6, whatever, we're going to fill in the missing data with 4. And so that's the backward filling. And so that is what this block is doing. And if any data is just 0, it gets rid of it. So it drops the data with duplicates and stuff that's going to skew our predictions. And this step is necessary for the creation of our matrix that you'll see. So now, constructing our matrix, this block of code is constructing matrix A with an intercept and price data as the independent variable. So the intercept and price data is the independent, and then our vector B, which is constructed with the return data, is our dependent variable. So here we go. Our price data is our independent, and our beta is our dependent. Now give me matrix with the beta. Okay. not Veta, vector, sorry. Beta vector. So 10, this is going to be solving our equation, and it's using linear regression with least squares once again as the alpha as the intercept, and then our beta now as the slope, not our vector b, the theta as our slope. And then now this is calculating our predicted return and our R squared. And these are just the equations for how it does it, and then residual, and then prints our information. So this is the returned output. And so I believe this information is completely false, at least in terms of a usability standpoint, but in terms of this class, if I didn't have ChatGPT, I would have known the difference, but I wouldn't have known how to fix it. So for the time being, I'm going to leave this as wrong. Because I got the code to run, but I believe the information is just not enough to base anything on. Price alone, as we've discussed in class, especially class this week, a lot more information is going to be needed to make a reliable prediction. And so digging into our numbers here, our alpha at basically 0 is constant in this regression model, and it's based on when price is returned as 0. Now the beta has once again, basically 0, is so small, which means that the price does not have a strong effect on returns. And so we would need to have more data to come to a more confident conclusion based on uh, the stocks we pulled. Getting into our residual of 9.541. This tells us how much error is in our prediction. And so with this number, this suggests that our model isn't very effective. And also with the results of our R squared being so low as well. Explains this being basically 0 explains practically nothing, and it doesn't give a good answer to the variability between your returns, which once again just reinstills that price alone wasn't enough. Good lesson to learn. And so our next block of code is going to be the calculating cap-in beta with pandas and NumPy. So here, I originally was going to use WRDS, but I used up my limits. I know there was another gentleman class that was having the same issue. And so what fixed it is just giving it some time to reset, because when I went onto the WRDS website, it didn't have any open queries. So for some reason, maybe it's because I'm using Google Colab, it wasn't communicating to WRDS in real time. And so I couldn't clear any of my previous code from the database. And so this originally wasn't working, but I was able to get it to supply some data after I gave it some time. And this is what I was referring to earlier as our stock data isn't giving me the ticker, which I feel like is kind of useless. I'd like to be able to see what I'm working with. And so that's room for improvement right there. Okay. And so now instead, I ended up using Y-Finance for this cap-in calculation. So these are the same. This code and this code are calculating the same thing, but for the purpose of this assignment, I used Y-Finance. So this, once again, installing our libraries. And 2, this is defining our variables. So I wanted to use the good old faithful GOEV canoe, absolute trash stock, and the market. index, market average. 3 defines my date range. This is fetching my data through YFinance when it's using the adjusted close column. Adjusted close column, which is stock price adjusted after splits and dividends. So calculating my daily return, this using the percentage change and adjusting closing prices. So there's our adjusted close, use percentage change, give me a little bit more reliable data to supply my daily market returns for my GOEV stock and for my market average. Now, merging my stock and market average returns. This merges the daily returns so that both of our data sets are in the same daemon frame, similar to what we did on the previous line of code or block of code, and giving me a usable date format. And once again, dropping the rows of missing data to make our end result more reliable. So now the big one, calculating our CAPM beta. This CAPM function gives us the covariance of stock returns and the market returns divided by the variance of market returns. And the beta covariance divided by variance market. It just quantifies the relationship between the two. So now 9 calculates the CAPM beta for our stock, which was the Canoo stock. Give me the beta. Now visualizing the scatter plot. I added this just to get a little bit more pretty data, to say the best. And so give me my scatter plot, title, labels, grids, all that. Make the plot, and then also add in a line of best fit just for that usability. And so here we go. Our CAPM of 2 for GOEV, which shows that it is 2 times more volatile than the market average, which is not a great thing. And so it's just very extremely unpredictable, especially with how wide of an array of data points we have, which this does solidify. I mean, what we expect when we look at this stock in particular, we knew that it's not good. Always hurts to see, but it's like a car crash. I can't look away. So now moving on to matrix operations. Here we go. Install data or libraries. Connect to WRDS. And here, oops, defining my date range using their database to fetch the data, stock, date, return. And so this uses, once again, the same SQL query to extract returns from their database and retrieve data using pandas. So this is where pandas is coming in handy. Restructuring the data. This once again is converting the date format so that we can manipulate it, reshaping said data using pivot functions so that each stock has its own column of daily returns. So that's just taking the data we pulled from WRDS and putting it into that usable format. Calculating the expected returns using that covariance matrix. This removes the missing values, provides the daily returns using the matrix to assess how stocks have relation to one another. And so now define my portfolio performance. This is using the return, volatility, and Sharpe ratio which the Sharpe ratio helps to measure how much return is earned via the amount of risk. And so there's our calculation. There's a calculation for the volatility, and there's our calculation for the return. Further optimizing our Sharpe ratio and putting it into a usable format using 0.03 as the risk-free rate. There is some constraints here. It must be 1 or 100% of our what am I trying to say? 100% allocation of our portfolio is what this weights must sum to 1 means. It needs to be between 0 and 1, so 0 to 100%. That's what this explains. Step number 6, performing optimization. And so this is taking our results and uses the sequential least squares programming to maximize our Sharpe ratio. This is just trying different combinations of portfolio weights to find the one that maximizes the risk-adjusted return. Greatest amount of risk, least amount, or greatest amount of reward to the least amount of risk. And then optimize my results, give me the one that is that best reward, least risk. Calculate optimized portfolio performance. This is just giving me our weight, expected return, volatility, and then a Sharpe ratio. So taking all the previous calculations and then supplying the actual answer. Now visualizing our efficient frontier, which just shows possible risk to return trade-off in a chart form. And I have it highlighting the best option with a red star, which is plot efficient frontier. Oops, stop. Calculates the frontier and then supplies me with my visual. So color red marker star gives me the optimized portfolio, and then it's a heat map also with the showing the various Sharpe ratios. The color gradient that represents higher ratios or the better risk adjusted returns shown in warmer colors. And so here we go. Here's our Sharpe ratio of 1.8780 and our efficient frontiers matrix. And so as we can see, expected return compared to volatility. We got crazy outlier right here. This is what I'll put it as the most optimized portfolio. I have my doubts about the legitimacy of this. That is a lot of volatility. And I don't know. For me personally, it's too volatile to consider that the most optimized option, but I'd like your input to clarify that. I would like to see something a little less volatile, even if that means taking less return, but that's just way too risky. And so this is my week 3 assignment, and thank you very much.